Why is it that every time scientists think they're standing at the doorstep of the ultimate truth, the door quietly vanishes? For more than a century, the greatest minds in physics have chased a single dream. One equation to rule the chaos, one framework that explains everything. Einstein thought he was close. String theorists once said they had it. Others swore quantum gravity would tie the final knot. Yet here we are, decades later, surrounded by dazzling technology, black hole photographs, and gravitational waves, and still no single theory that unites the forces of nature. It sounds so simple on paper, one elegant line of math that could explain why galaxies spin, why atoms cling together, and why we even exist at all. It would be the crown jewel of human thought, the answer behind every answer. But each time we reach for it, the universe slips through our fingers like smoke. The equations break. The experiments disagree. And nature, in its quiet way, refuses to be cornered. Maybe the problem isn't that physicists aren't clever enough. Maybe the problem is deeper, that reality itself resists being reduced to a single note. Still, we keep chasing it, because to give up the search would be to accept that the universe is a puzzle with missing pieces. And no scientist can live peacefully with that idea. Every failure leaves behind a new clue, a sharper tool, a better question. That's why the hunt never ends. The theory of everything isn't just a scientific ambition. It's a mirror held up to our own nature. Our refusal to stop asking why. Over the next few moments, we'll step through that story. From ancient philosophers who saw the world in fire and water, to Newton's clockwork heavens, to Einstein's curved space-time and the wild quantum world that shattered his faith in order. We'll see how every generation built a version of everything, only to watch it crumble under the next discovery. And maybe, by the end, you'll see what many scientists have quietly begun to suspect, that the dream of a perfect theory might be the most human illusion of all. But before we dive in, take a moment to imagine it. A world where every mystery can be traced back to one pattern, one principle, where time, gravity, light, matter, all the chaos, reduced to a single rhythm. That vision has haunted thinkers for millennia. It's kept entire departments awake at night, staring at chalkboards long after the lights should have gone out. Because if that theory exists, even if it's impossibly far, it would be the ultimate key to understanding not just the universe, but ourselves. Still, the closer we get, the stranger the road becomes. Equations that start clean spiral into infinities. Particles appear and vanish like rumors. Space and time, the stage we thought we stood on, begin to wobble beneath our feet. And yet, we keep walking. Maybe that's the point. Maybe the real meaning of science isn't to reach the final answer, but to discover how deep the questions go. So tonight, as we follow this trail, from Newton's apple to the edge of black holes, from quantum dust to the whispers of gravitational waves, remember this. Every failure in physics is also a message, a reminder that the universe is bigger than our diagrams, stranger than our equations, and far more patient than we are. This is the story of that endless pursuit, the dream of total understanding, the heartbreak of every collapse, and the quiet beauty in never being done. The hunger to find one truth behind everything didn't begin in the age of telescopes or equations. It began long before science had a name. Thousands of years ago, people looked at lightning, rivers, and the stars, and felt that there had to be a single thread holding it all together. Some said that thread was water. Others swore it was fire or air or some unseen essence that lived inside every stone and cloud. They didn't have laboratories, only wonder. But that same instinct still drives physics today. The feeling that the chaos of the world must come from one quiet order beneath it. Centuries later, that idea took its first real shape in the hands of Isaac Newton. He watched apples fall and planets move and dared to say they followed the same law. For the first time, heaven and earth were written in the same language: motion, mass, and gravity. To people of his time, it was like discovering that the rules of gods and men were one and the same. An apple dropping from a branch and the moon tracing its orbit were no longer two stories. They were one story told with new mathematics. Newton gave humanity its first taste of unification. The world felt predictable, clean, and almost mechanical. A cosmic clock ticking with perfect precision. But perfection never lasts long in science. As the tools sharpened, the cracks began to show. Mercury's orbit drifted where Newton's math said it shouldn't. Light bent in strange ways that didn't belong to any formula. Something deeper was hiding behind the curtain. Then came a quiet man with wild hair and a notebook full of impossible thoughts. Einstein didn't patch Newton's laws. He rebuilt the stage itself. He told us gravity wasn't a mysterious pulling force at all. It was space and time themselves bending around matter, like a fabric stretching under weight. Planets didn't circle the sun because something dragged them. They moved along curves drawn by the shape of reality. It was a revelation. And yet for Einstein, it wasn't enough. He couldn't stand that there was still a second rulebook, the new and unpredictable quantum mechanics, describing the tiny world inside atoms. He wanted one set of principles that could explain the universe from galaxies to electrons, from the grand to the grain. He spent the last decades of his life chasing that dream, what he called the unified field theory. But there was a problem. Quantum mechanics didn't care about certainty. It lived on chance, probability, and waves of maybes. Einstein's universe was smooth and elegant. The quantum world was jumpy and chaotic. He simply couldn't believe that reality itself might roll dice. That conflict, between beauty and randomness, between the smooth and the granular, would shape physics for the next century. And when Einstein finally passed away, his notebooks were filled not with answers, but with trails that vanished mid-equation. Still, his failure wasn't meaningless. It left behind a warning written in chalk. Maybe nature doesn't want to be compressed into a single page. From the first philosophers to Newton to Einstein, the melody has been the same. A yearning to see the world as one story. And every time we think we've written the final verse, the universe adds another instrument to the orchestra. That's where our journey truly begins, at the point where one man's obsession with unity turned into humanity's endless chase for a perfect theory. To understand why every grand theory eventually collapses, we have to step into the divide that split physics in two. On one side stands Einstein's masterpiece, general relativity. It paints the universe as a smooth fabric, an endless stage where galaxies and stars drift across curved geometry. Here, gravity isn't a mysterious force at all. It's the bending of that stage itself. Matter tells space how to curve, and curved space tells matter how to move. Everything flows with elegance and order, like planets sliding along invisible rails carved into space-time. Relativity is majestic. It describes black holes, the orbit of Mercury, the ticking of clocks at different altitudes, and even the faint ripples we now call gravitational waves. A century later, not a single precise test has broken it. But walk a little closer to the atomic world, and that calm stage collapses into chaos. At the smallest scales, the laws change entirely. Particles blur into clouds of possibility. Locations smear into probabilities. Welcome to quantum mechanics, a universe where chance rules and certainty dies. In this realm, an electron can be everywhere at once until you look at it. Two particles can become entangled, their fates woven together instantly, no matter the distance. Things can tunnel through barriers that should be solid. It's a world that doesn't care about common sense, only about the strange logic of probabilities. And yet, this strangeness works. Every chip in your phone, every laser, every MRI machine, all of it runs on quantum principles. It's not just theory, it's reality, proven a billion times over. But here's the problem. Einstein's equations rule the large. Quantum mechanics rules the small. Neither knows how to speak the other's language. Most of the time, that's fine. If you're calculating a satellite's orbit, you use relativity. If you're designing a transistor, you use quantum physics. Each does its job beautifully, until you reach a place where both must apply at once. Inside a black hole. At the birth of the universe, moments where space-time bends infinitely and matter shrinks to nothing. That's where the math explodes. Relativity gives you singularities, points where everything becomes infinite. Quantum mechanics gives you fluctuations that make space itself shimmer like static. Try to merge them, and the equations scream back. Nonsense, infinities, contradictions. Physicists call it the incompatibility problem. It's like trying to merge two masterpieces painted on different canvases, beautiful separately, incoherent together. Einstein's universe is continuous, smooth, and deterministic. The quantum world is granular, jumpy, and built on uncertainty. Each rests on foundations the other rejects. It's as if reality itself uses two operating systems that crash whenever you try to run them on the same machine. That's why the search for a theory of everything is so difficult. It isn't just a puzzle of numbers. It's a philosophical collision. Two visions of existence that refuse to fit. And yet somewhere out there, the universe clearly reconciles them. Black holes exist. The Big Bang happened. Nature itself found a way to let both rules coexist. We just haven't found its manual. The next question physicists faced was, if quantum mechanics unites three of nature's forces beautifully, why does gravity, the oldest and most familiar, stand apart like an outcast? That's where the story leads next. To the rebel force that refuses to join the family portrait. If the universe were a classroom, three of nature's forces would sit together at the same table. Electromagnetism, the weak force, and the strong force. They share notes, speak the same language, and all obey the rules of quantum mechanics. They form what scientists proudly call the Standard Model. A framework so successful that it can predict the tiniest flickers inside a particle accelerator with ridiculous precision. But at the back of the room sits gravity. Quiet, stubborn, and different. It doesn't fit in. Gravity still insists on using Einstein's geometry, curved space, and flowing time, while the other three play by quantum rules. And that has driven physicists crazy for decades. They tried to invite gravity into the quantum club. They imagined a particle that could carry the force, just like photons carry light. They called it the graviton, an invisible messenger of attraction that would glide through space at the speed of light, tugging everything with it. It sounded elegant, but when they ran the numbers, the math blew up into infinities that refused to cancel. Predictions dissolved into nonsense. The universe simply didn't cooperate, so others took a different path. They suggested that maybe space itself isn't smooth at all. Maybe, at the smallest possible scale, it's made of tiny loops, a woven fabric of quantum threads. That's loop quantum gravity. Zoom in far enough and space would look pixelated, like an old photograph revealing its grid. Beautiful idea, except it explained gravity, but not the other forces. Once again, the puzzle refused to come together. Then came the radical thinkers who flipped the problem upside down. What if gravity isn't a fundamental force at all? What if it's something that emerges, like temperature emerging from trillions of moving atoms? No one speaks of temperature particles after all. It's a collective behavior. By that analogy, maybe gravity is not born from particles, but from the way quantum information connects and entangles everything. If that's true, then chasing a graviton might be like chasing a mirage. Nowhere does this outsider status of gravity show more brutally than inside black holes. According to relativity, a black hole is simple, a point where space-time curves so steeply that not even light can climb out. But when quantum physics enters the picture, simplicity dies. Stephen Hawking showed that black holes aren't perfectly black. They leak faint radiation. That means they can evaporate over time. A shocking thought. But evaporation brings a paradox. If a black hole disappears, what happens to the information about everything that fell in? Relativity says it's gone forever. Quantum mechanics says information can never be destroyed. Both can't be right. Once again, gravity breaks the peace. The same clash appears at the opposite end of time, the Big Bang. Relativity predicts a singularity, an infinite point where physics collapses. Quantum theory screams that such infinities can't exist. Something must give, but we don't know which. That's why physicists call gravity the problem child of unification, the one force that refuses to play by the same rules. It's the reason every theory of everything eventually hits a wall. Ironically, the very force that holds the universe together is the one tearing our equations apart. And that is where a new hope once arose. A theory that promised to bring peace to this family feud. A vision of vibrating strings that could make every force, even gravity, hum to the same tune. For a moment in time, it felt like physics had finally found its missing key. A theory so elegant, so complete, that even gravity would bow to it. That key was called string theory. It began with a simple but revolutionary thought. Maybe the smallest pieces of the universe aren't dots at all. Maybe they're strings, tiny, vibrating threads of pure energy, far smaller than any atom, so small that even the best microscopes in existence could never glimpse them. In this vision, everything, every particle, every force, is born from the way these strings vibrate. Change the vibration, and you change the identity. One frequency becomes an electron, another becomes a quark, another could even be a graviton, the particle of gravity that Einstein never found. Suddenly, everything we know could be music. The universe itself, a vast cosmic symphony. It was irresistible. The equations were graceful. The idea was poetic. For once, all the pieces seemed to sing in harmony. By the late 20th century, string theory wasn't just a theory, it was a movement. Entire departments dedicated their lives to it. Books promised the final theory. For a generation of physicists, this was the Holy Grail. But then, as always, beauty met reality. And reality was not impressed. The first problem was space itself. String theory only worked if the universe had more dimensions than we can see. Not 3 of space and 1 of time, but 10, sometimes even 11. The extra dimensions, it said, were still there, just curled up so tightly that we can't detect them. Like threads woven deep into a fabric, invisible from a distance but essential to its structure. Mathematically, it made sense. Experimentally, nothing. No sign, no proof, no measurement. Then came an even stranger twist. The landscape problem. Instead of predicting one neat universe, the equations of string theory allowed for an almost infinite number of possible universes, each with its own laws, its own constants, its own rules of physics. The dream of one perfect blueprint had turned into a library with countless blueprints, and no way to know which one matched our world. It was like searching for a single treasure map, only to find 1,000 maps drawn in the same ink. All beautiful, all possible. But which one was real? Some physicists tried to fix the problem by invoking the multiverse, the idea that maybe all those universes exist, and we just happen to live in the one that allows life. It was a clever escape, but it came with a cost. If you can't test it, if you can't prove or disprove it, is it still science? For a while, string theory felt untouchable, beyond criticism, too beautiful to fail. But as decades passed and experiments found nothing to support it, doubts began to grow. Maybe the elegance of the math had seduced us. Maybe the music was only playing in our imagination. Yet even in its disappointment, string theory left behind gifts. It built bridges between geometry and quantum fields. It gave rise to M-theory, an even larger framework that tied different versions of string theory together. It helped us understand black holes in new ways, and inspired tools still used in other fields of physics. So it wasn't a dead end, just a detour. But the dream of a single perfect theory was fading. String theory had everything: elegance, beauty, ambition. Except one thing: evidence. After decades of chasing equations, physicists began to look somewhere new, not to blackboards but to laboratories. If the math wouldn't give them answers, maybe the universe itself would. Because theories can seduce you, but only experiments can tell you the truth. After decades of paper dreams and mathematical castles, physics began to change direction. It turned its eyes from chalkboards to the laboratory. Because at some point, the numbers weren't enough. If the ultimate theory existed, it had to leave fingerprints, tiny marks in the real world that we could measure, not just imagine. And so began the quiet revolution, the age of quantum gravity experiments. The challenge was brutal: Gravity, for all its cosmic grandeur, is laughably weak at the microscopic scale. Take a paperclip and hold it above the ground. The small magnet on your refrigerator easily beats the gravitational pull of the entire planet. That's how feeble gravity becomes when you zoom in. So how do you test something that weak at the quantum level? You start with creativity. One of the boldest proposals is the entanglement test. In quantum mechanics, when two particles become entangled, they share information instantly. Their fates intertwined no matter how far apart they drift. So what if two tiny objects could become entangled only through gravity? That would mean gravity itself must follow quantum rules. Imagine this. Two spheres of matter, each smaller than a grain of sand, suspended in a vacuum colder than deep space. They sit perfectly still, shielded from every vibration, every magnetic field, every whisper of outside noise. You bring them close enough that the only way they can sense each other is through their mutual gravity. If their quantum states link, if they become entangled, that would be the first direct sign that gravity isn't purely classical. It would mean gravity itself is quantum. That single observation would rewrite physics overnight. But the difficulty is staggering. The setups must be so precise that even the heartbeat of the planet can ruin the test. The hum of passing cars, the faintest tremor, the flicker of a nearby electrical current, all of it can blur the signal. It's like trying to hear a whisper at a rock concert. Other experiments take a different approach. They test gravity's strength at microscopic distances, smaller than the width of a human hair, to see if it begins to behave strangely when things get too close. If the familiar inverse square law starts to wobble, that might hint at hidden dimensions or unknown physics lurking just beyond reach. Some setups look like something from science fiction. Tiny metal plates balanced so delicately that a speck of dust can throw them off. One team even built a miniature seesaw so sensitive that a single microscopic bead could tilt it. To measure forces trillions of times weaker than a magnet's pull, that's the level of precision we're talking about. And then there's the cosmic frontier, using the universe itself as a laboratory. Black holes, neutron stars, the cosmic microwave background. They're nature's own experiments where gravity and quantum effects collide. If we ever detect Hawking radiation or subtle quantum fingerprints in cosmic data, it could be the smoking gun we've been searching for. None of this is easy. Each attempt feels like balancing on the edge of impossibility. But even the act of trying has changed physics. For the first time in history, we're not treating quantum gravity as a thought experiment. We're building machines to test it. The blackboard has finally met the bench, and that shift matters. Because if these experiments detect quantum gravity, we'll know the universe runs on one set of rules after all. If they don't, it means we've been staring at the wrong assumptions since Einstein's day. Either way, it's progress. Either way, we learn something deeper about the code that runs reality. For over a century, physicists dreamed of unification. Now, for the first time, they can reach for it. Not through imagination, but through instruments, and the universe has just begun to answer. For 100 years, Einstein's equations predicted something almost unbelievable, that when massive objects like stars or black holes collide, they send ripples through space itself. Not through air, not through sound, but through the very fabric of the universe. Those ripples are called gravitational waves, and for most of the 20th century, they were just theory, invisible, untouchable. Then, in 2015, humanity heard them for the first time, a faint whisper in the data. Two black holes colliding more than 1 billion light-years away. It was a sound so quiet, it moved a mirror by less than 1/10,000th the width of an atom. Yet in that whisper was proof that Einstein had been right. Again. At first, scientists celebrated it as confirmation of relativity. But soon they realized gravitational waves could be something more. A testing ground for every theory of everything that's ever been written. You see, black holes and neutron stars are nature's own laboratories. They crush matter and space-time together so violently that quantum mechanics and gravity are forced to meet. If there's a crack in Einstein's theory, if the universe hides a deeper layer, that's where it would show up. Each time a new gravitational wave is recorded, physicists dissect it like detectives studying a cosmic crime scene. They look for distortions, subtle echoes that shouldn't exist, tiny delays, unexpected vibrations. Because in some rival theories, gravitational waves should behave differently. They should come in extra flavors, carry hidden polarizations, or move at slightly different speeds. But so far, every single time, Einstein wins. The waves behave exactly as his century-old equations predicted. No extra signals, no deviations, perfect symmetry, perfect silence. It's both inspiring and deeply frustrating. Because every time relativity passes another test, it leaves less room for new physics to grow. It's like polishing a perfect glass sphere, hoping to find a crack, and realizing it's flawless. Yet physicists aren't giving up. They're building new detectors, more sensitive than ever, machines that can pick up ripples from deeper in space and further back in time. Because the early universe was filled with these waves, a cosmic hum left over from the first seconds after the Big Bang. If we can catch that background, buried beneath the noise of all the others, we might hear new harmonies, signs of forces or particles we've never known. It's a strange paradox. The more precisely we test Einstein, the more indestructible he becomes. But hidden in that perfection might be the clue we're missing. Because even a flawless melody can hide a note we can't yet hear. Gravitational waves have changed physics forever. They've turned the sky into an instrument, a way to listen to the universe instead of just watching it. And with every new detection, we're not just confirming Einstein. We're interrogating him. We're asking again and again, are you sure this is the whole truth? So far, the answer has been yes. But one day, maybe soon, a wave will arrive that doesn't fit the pattern. A ripple that bends the rules. And when that happens, it won't just be Einstein's equations that shift. It will be our entire understanding of reality. Because in the music of the cosmos, even one wrong note can change the entire song. There's a strange weakness that hides inside science, one that even the sharpest minds fall into. It's not pride. It's not arrogance. It's beauty. Equations, like art, can be beautiful. When they fit together with perfect symmetry, when the math feels effortless, physicists describe it like music. Einstein once said that a good theory should be beautiful. And for a long time, history agreed with him. Relativity, beautiful. Maxwell's equations, beautiful. Even the Schrödinger equation, elegant and clean. Over and over, nature seemed to reward elegance with truth. Until it didn't. Because somewhere along the way, physicists started chasing beauty more than they chased reality. They began to trust the perfection of the math more than the mess of the data. The best example? Supersymmetry. For decades, it was the darling of theoretical physics. The idea was simple, stunning, and mathematically precise. Every particle we know has a heavier, super partner. Quarks have squarks. Electrons have selectrons. Neutrinos have sneutrinos. It tied everything together into one balanced whole. It even offered answers to deep mysteries. Dark matter, the stability of the universe, the Higgs boson. It was, quite literally, too perfect. So perfect that physicists built the Large Hadron Collider, the biggest machine ever made, partly to find it. They expected supersymmetric particles to appear quickly, right there in the data. But when the first results came in, nothing. And the next runs? Still nothing. No superpartners, no elegant symmetry waiting beneath the surface. Reality, once again, refused to care about our sense of design. It wasn't the first time beauty had led us astray. The ancient Greeks imagined the heavens as perfect circles because circles felt divine. But the planets betrayed them. Their orbits were messy ellipses. Nature had chosen function over form. Today, the same danger still looms. String theory, supersymmetry, grand unifications. They all shimmer with mathematical grace. But the universe doesn't owe us elegance. It only owes us truth. The trouble is, physicists are human. We crave order. We want to believe that beneath all this chaos, there's a perfect pattern waiting to be uncovered. But what if there isn't? What if the truth is untidy? Patchwork, irregular, and strange. What if the universe is less like a polished diamond and more like a tangled web? Rough, asymmetrical, but still profoundly real. That's the painful lesson of the past few decades. Beauty doesn't guarantee truth, and truth doesn't have to be beautiful. Einstein himself fell into that trap. He rejected quantum mechanics because he found its randomness ugly. He wanted a universe that made sense, one that followed reason like clockwork. But the universe didn't follow reason. It followed probability. And that messy, unpredictable framework now powers every laser, transistor, and atomic clock on Earth. So maybe the real wisdom isn't in chasing elegance, but in learning to live with imperfection. To love the crookedness of reality, because that's where truth hides. Physics advances not because it's pretty, but because it works. Sometimes the math sings, sometimes it stutters, but what matters is whether nature sings back. When people talk about the failures of modern physics, it sounds like a story of disappointment, a century of false starts and broken dreams. But that's not the real picture. Because in science, failure doesn't mean you went nowhere. It means you found a new path by walking the wrong one first. Every collapsed theory leaves behind something useful, a tool, a principle, or an idea that changes how we see the world. The journey toward a theory of everything has given us more progress than most people realize. Not the final formula, maybe, but fragments of truth that have become entire branches of physics on their own. Take the conformal bootstrap program. It began as an abstract dream in the 1970s, a way to understand the quantum world without writing down every messy detail. Instead of solving for every variable, the bootstrap focused on what must be true for any consistent universe to exist. Rules of symmetry, rules of logic. It was like solving a jigsaw puzzle without ever seeing the picture. You just know how the pieces have to fit. Decades later, this idea exploded into one of the most precise tools in modern theoretical physics. With it, scientists can predict the properties of quantum fields to almost absurd accuracy. Not by brute force, but by pure reasoning. That's not failure. That's evolution. Then there's the field of scattering amplitudes. Every time two particles collide inside an accelerator, they exchange energy in a flurry of chaos. For years, calculating those interactions was a nightmare. Thousands of terms, miles of math. But physicists started to notice hidden simplicity beneath the chaos. They found ways to describe those collisions using shapes. Elegant geometric objects called polytopes. Imagine turning a fistful of equations into a single, luminous image. That's what they achieved. The math didn't just shrink, it sang. And then there's the most poetic of them all. Holography. Juan Maldacena's ADSE's CFT correspondence. A name that sounds impossibly technical, but carries a breathtaking idea. It suggests that a universe with gravity inside it can sometimes be exactly mirrored by a universe without gravity on its boundary. In other words, everything that happens inside a volume of space can be described by information painted on its surface, like a cosmic hologram. It's a new way of seeing reality itself, as if the entire universe might be a projection of deeper information we can't yet touch. Each of these breakthroughs came from theories that never reached their promised land. Each is a shard of the larger mirror we're still trying to piece together. Maybe that's what progress really looks like in physics. Not one big leap to the top, but 1,000 small climbs that slowly build the mountain. Because while string theory may not have delivered its grand finale, it gave us tools we now use everywhere, from condensed matter physics to mathematics. Loop quantum gravity may not unify the forces, but it taught us how to see space-time as something that might be woven, not built. Holography may not be the last word, but it gave us a glimpse of how gravity and quantum mechanics might be two reflections of one truth. Science doesn't stand still because of failure. It stands taller because of it. Every dead end leaves a trail marker. Every wrong turn becomes a road someone else will walk more wisely. And maybe, just maybe, the final theory won't arrive all at once, but through the slow merging of these fragments, a mosaic of ideas that together form the bigger picture we've been chasing all along. There's a quiet question hiding underneath all of physics, a question most scientists prefer not to ask out loud. What if a theory of everything doesn't exist? It sounds like heresy. After all, every century of discovery, from Newton's gravity to quantum fields, has been driven by the belief that nature follows rules, that all the chaos, all the randomness, can be reduced to a single pattern. But what if that belief itself is the illusion? When physicists talk about the theory of everything, they imagine one elegant framework that explains every force, every particle, every interaction in the cosmos, one book of laws written in the language of mathematics. But that dream might say more about us than about the universe, because we, as humans, love closure. We like clean endings and tidy answers. We want the universe to make sense, to feel complete. But nature doesn't seem to care about our craving for simplicity. It keeps giving us exceptions, paradoxes, and mysteries that don't fit the pattern. Even mathematics, the most precise tool we have, contains its own boundaries. In the 1930s, the logician Kurt Gödel proved something shocking. In any logical system rich enough to describe numbers, there will always be true statements that can't be proven within that system. No matter how perfectly you define your rules, there will always be truths hiding outside them. If that's true for math, the cleanest language we know, why wouldn't it be true for physics? Maybe there will always be truths about the universe that lie just beyond the reach of our equations. Then there's another problem: the meaning of everything. When we say theory of everything, what do we actually mean? Does everything stop at atoms and forces? Or does it include life, mind, time, consciousness, all the strange layers that appear when matter starts to think about itself? The deeper you stretch that definition, the less likely it becomes that one formula could hold it all. Maybe the universe isn't built on one rule book. Maybe it's made of layers, each with its own laws. Physics at one level, chemistry at another, biology beyond that. Each layer obeys the one beneath it, but speaks its own language. Just as you don't need to mention DNA when describing an electron, maybe the cosmos doesn't need one master equation to keep it running. And then there's the hardest truth of all. Maybe the limits aren't in nature. Maybe they're in us. Our brains evolved to throw spears, not to understand quantum gravity. We've stretched our imagination with math and technology, but there may be ceilings to what we can ever truly comprehend. A dog can't understand calculus, no matter how smart it is. What if the universe is running on concepts that are just as far beyond our reach? It's not a comfortable thought, but it might be the most honest one. Even so, the search still matters, because every time we fail to find the final theory, we find something else. A deeper humility, a sharper tool, a clearer picture of where the mystery begins. Some physicists, like Sabine Hossenfelder, have argued that maybe we should stop obsessing over unification, that we should accept the universe as patchwork, messy, irregular, but still describable piece by piece. Others refuse to give up the dream, pointing out that history has always rewarded unifiers. Newton, Maxwell, Einstein. Why stop now? Two philosophies, forever in tension. One says, keep climbing. There's one mountain, one summit. The other says, there are many hills, and the view from each is enough. Maybe both are right. Maybe progress doesn't need a finish line. Maybe the real purpose of the journey is to keep deepening the question, not to erase it. Because if the universe really is infinite in depth, then understanding it fully isn't our destiny. It's our privilege to keep trying. When a question refuses to break after decades of effort, you start wondering if you've been asking it the wrong way. That's where physics stands now. After centuries of trying to unite all the forces, some scientists are beginning to ask, what if the universe doesn't want to be unified in the way we imagine? Instead of forcing old equations to fit, a new generation of thinkers is turning the problem inside out, starting not from matter or motion, but from information. One of the boldest shifts is the idea that space and time might not be fundamental at all. What if the fabric of reality, the very stage where everything plays out, isn't the foundation, but an illusion that emerges from something deeper? Think of temperature. There's no such thing as a temperature particle. Temperature is what happens when trillions of atoms move and collide together. It's a property that appears when you zoom out. Now imagine the same is true for space-time itself. Maybe space and time are not ingredients. Maybe they're the texture that appears when quantum information links together. Physicists like Mark van Ramsdonk and Eric Verlinde have taken this idea seriously. They suggest that gravity and space-time might rise out of the quantum entanglement between invisible bits of information, that the universe, at its core, might be woven from relationships, not objects. It's a radical thought, that reality is less like a structure and more like a web of communication. Then there's the holographic principle, an idea that sounds like science fiction but has serious math behind it. It says our entire three-dimensional universe could be described by information encoded on a two-dimensional surface, like a hologram projected from the edges of reality itself. It's not just poetic. In certain models it works. It's as if everything we see and touch is a shadow of deeper equations playing out on a boundary we can't perceive. Another approach, called the causal set theory, goes even further. It imagines space-time as a network of discrete events connected by cause and effect. Not continuous, not smooth, just a cosmic web of who influenced what. Zoom out far enough, and the chaos looks like smooth space. Just like a beach looks like a solid surface until you notice it's really made of grains of sand. And then there's twistor theory, dreamed up by Roger Penrose, a reimagining of physics built not on space or time, but on the geometry of light itself. In twistor space, the universe isn't a grid of positions and moments. It's a pattern of relationships defined by the paths that light can take. It flips our perspective completely. Instead of space and time defining motion, motion defines space and time. Of course, no revolution in science comes without its wilder cousins. Among them sits the simulation hypothesis, the idea that the reason we can't unify everything might be because the universe isn't the base layer of reality at all. Maybe we're studying the rules of a simulation, a cosmic program so perfect that the code itself is the physics we call laws. Most scientists don't treat it as a literal theory. It's impossible to test, at least for now, but it lingers in the background as a thought experiment. What if the glitches we see in our equations are signs that we're studying a system built on rules not meant to be unified? Across all these ideas, emergent spacetime, holography, causal networks, twistor geometry, even simulation, there's a common theme: the willingness to break the old assumptions, to stop asking, how do we glue quantum mechanics to relativity, and start asking, what if the glue itself is an illusion? Still, these ideas share one old challenge: proof. For now, they live in mathematics, not measurement. They stretch the imagination, but until we can test them, in a lab, in space, or in data, they remain philosophical guesses wearing scientific suits. And yet, this shift matters, because it shows that physics hasn't gone stale. It's not trapped in equations from the past. It's evolving, questioning its own foundation. Sometimes, to move forward, you have to let go of what you thought was real. Maybe the next breakthrough won't come from uniting two old theories, but from realizing they were never truly separate in the first place.